Hi everyone, welcome back to 3 Deviations. In today's video, we're going to start fooling around with infinite series. So we are going to start with geometric series. So geometric series are really easy because we only need to apply elementary limits and algebraic formulas in order to find what we're looking for, which is not going to be the case in future tests for divergence. So anyways, with the geometric series, we know how those work. We know that the series is predicated on some sort of ratio. So we have a sum. We have a sum of a sub n, and we're going from n equals 1 to infinity. And a sub n is equal to some beginning number, a sub 1. Or we may even call that just a, since it's not really important that we put the subscript 1 on it, times a common ratio to the n minus 1th power. Okay, so that's how our geometric series work. So now we're going to be looking at how these behave when they go to infinity. So we're actually going to start by what our formula actually means. How to find a sum, because this is very important because the geometric series is one of the series that we can find convergence, and then in addition to finding convergence, we can find exactly what that series converges to. That's not going to be the case with a lot of the other series that we look at. We're only going to be able to determine that it converges, and we're only going to be able to determine maybe some estimates about what it converges to. But with geometric series, we can always determine what it converges to as long as the series converges. So we talked about the nth partial sum of a geometric series being a times 1 minus r to the n over 1 minus r. Okay, so now instead of having n, we are going to have infinity. So the infinite partial sum is equal to the limit as n approaches infinity of a times 1 minus r to the n over 1 minus r. Okay, so first, we're going to need some algebraic manipulation to do this limit. So that we're going to try to isolate that r to the nth power. So that's the only thing we have an n in, right? So we will multiply everything by a on the top, so you get the limit as n approaches infinity of a minus a times r to the n over 1 minus r. Now what we can do is we can split this little fraction guy up. We have one term in the numerator here, we've got another term there, we can split it up, and then we can even take this, so this is going to be equal to a over 1 minus r minus a r to the n over 1 minus r, but we can actually take that r sub n out, and we're going to put that in its limit by itself, so we get a over 1 minus r minus a over 1 minus r times the limit as n approaches infinity of r to the n. Great, this is exactly what we want, because now what we have is we have our r sub n isolated. So we need to think about for what values of r is, because essentially what we want, in order for this to be finite, this term needs to go away. So we need r to the n to be 0. So for what value does r to the n go to 0? For what value of r? So if r is bigger than 1, then r is going to get increasingly bigger as we approach infinity with n. However, if we get closer and closer to 0, if I do like r to the 1/2, then r to the, if I keep doing r to the 1/2, 1/2 to the infinity, if we keep doing that, then we're going to get closer to 0. And it's interesting because it actually also works for negative numbers. So if r is raised to a negative number, then, or if a negative number is raised to infinite power that's smaller than -1, then we're also going to go to 0. But as soon as we get with, as long as our magnitude is larger than 1, our absolute magnitude is larger than 1, then we are in trouble. And the interesting case is that if r is equal to 1, then we're also going to have a problem, because if we keep raising 1 to infinite powers, then that's going to go, then that's not going to go to infinity, but it's also not going to go to 0. So then we're going to have another problem on our hands. And in that case, we are going to be looking at something called the harmonic series, which is the sum from n equals 1 to infinity of 1 over n. And that actually turns out to diverge. So we'll look at that. But anyways, for our infinite partial sum, we get a over 1 minus r, given that the absolute value of r is less than 1. So that allows us to find the sum of a geometric series. So we also briefly touched upon the test for divergence yesterday. So that said that if the limit as n approaches infinity of a sub n is not 0, then the series diverges. So that's an easy way. This doesn't only apply to geometric series, but if I have any series, I can plug a sub n into a limit as n approaches infinity, and if that guy isn't 0, then we diverge. Now this is probably the most useful test that we use in sequences and series. Okay, so now let's move on to an example. So for this example, I would like us to show that this series diverges. Now it doesn't matter if this series is geometric or not, but we can use the test for divergence. So all we need to do is we just need to plug this guy, we just need to plug that guy into a limit. So if we take the limit as n approaches infinity of 2 to the 2n times 3 to the 1 minus n, it's obvious that this guy's going to shoot up. It's not going to be 0 because we are raising this to a positive power, we're raising this to a positive power, and they're multiplied together. So this is going to grow up like crazy. We're multiplying two exponential functions together. And as we get to infinity, you can imagine this as an a sub n versus n plot. So an a sub n versus n plot, this guy is going to be a huge exponential function. That probably was even a little bit less than what it actually is. It probably is a lot more like that. But this exponential function is obviously going to diverge, and our limit is not 0. Thus, our series diverges by the test for divergence. So that's what we say at the end of all of our little proofs. We say that the series diverges by whatever test we're using. In this case, we use the test for divergence because we said that the limit isn't 0. Okay, so now let's look at another example. We're going to use that formula that we used earlier. So I want us to find the sum of the series 1/2 plus 1/4 plus 1/8 plus 1/16, and so on and so forth. Okay, so we can obviously see a pattern in the denominator. We keep multiplying everything by 2. So the lowest thing on the denominator is just going to be 2 to the n. So we get the series from n equals 1 to infinity of 1 over 2 to the n. Okay, so first let's make sure that this guy converges. So if I take the limit as n approaches infinity of 1 over 2 to the n, then it is going to be equal to 0, obviously, because this is going to get smaller and smaller and smaller. If we have 1 over 2 to the infinity, I'm doing bad math notation here, we should never do the infinity there, but that's roughly equal to 1 over infinity, which is equal to 0. Okay, so now we know that we can use our sum formula that we looked in the last video. Now our common ratio is going to be 1/2, and our first value is also 1/2. So we get 1/2 over 1 minus 1/2, and so we get 1/2 over 1/2, which is 1. So it turns out if you keep adding all of these together, then you get 1. And I think that's pretty cool because you're adding infinite things together, but it's turning out to be something that isn't infinite at all. And if you want to start this series at 0, n equals 0, then you're just going to be adding 1 as to the beginning of it, and that'll give you 2. There's a lot of very interesting math puzzles involving this series. It's a very interesting topic. Anyways, in the next video, we're going to be talking about telescoping series. So that's kind of like an extension of what we're talking about now, but we're going to need to employ some partial fractions in order to solve our series. Then we are going to be looking at some other tests for divergence, and then we'll be off to Taylor and Maclaurin. All right, we'll see you in the next one. Bye.